Welcome to Chapter 2. Chapter 2 is on percentages, graphs, and measures of central tendency. All of those are descriptive stats. So as you remember from Chapter 1, there's those two broad categories of statistics, descriptives and inferential. In this beginning portion of the semester, we're covering descriptives. And so these are our first set of descriptive stats. And remember that descriptive stats describe a sample. And so they're going to give us values that summarize all of the data within our data set. And then graphs, of course, are visual representations of that. And so we'll learn how to create a couple different graphs in this chapter as well. So here we go. Okay, so the first descriptive stat that we're going to use is percentages. And percentages are perhaps one of the most popular statistics that are reported in any field, in articles, in sports, in every politics, in all areas of our life. So percentages is a really important and popular descriptive stat. However, it's super easy to manipulate the impression a percentage gives. And so the way you can do that is kind of just by excluding the denominator. So if you give a percentage, it can be really misleading if you leave out the population size or whatever the denominator information would be. So for example, if I were to tell you that I surveyed my students and 100% of them said that they love statistics, that might be kind of a surprising percentage to you. It is accurate, but however, it's not really representative of everyone or most people's opinions if I only asked two students that both had A's, right? So if I asked two students that both had A's how they liked my class and they both said they love statistics, and I say, well, there you go, 100% of students I asked love statistics. It's true, but it's misleading. And so in this particular point of the lecture, we are going to learn to do the following things with the percentage worksheet. So you're going to need to go to Canvas, and in this module, you are going to pull the percentage worksheet out and have it handy as we go through this together. So in that worksheet, we're going to learn to calculate a percentage, calculate the percentage of a total, calculate changes in percentage, and calculate per capita rates. This is the percentages worksheet, and we're going to learn several different skills with percentages, like how to calculate a percentage, how to find the percentage of a total, how to calculate per capita, and percentage changes. So the first one that we're going to do is number 1. It's always a good place to start. And so in order to solve actually number 1 as well as number 2, 3, and 4, I'm going to teach you a little trick that I use. It's super easy and it helps you to kind of break down word problems in a way that's manageable. So the trick is up here. I wrote it at the top of my worksheet. And so what you want to do is write percentage over 100 equals the word is over of. And so we're going to just use our word problem to fill in those missing puzzle pieces, and that will get us our answer. So I'll show you what I mean. So for number 1, it says, if there are 6 males in a class of 20, what is the percentage of males? And so I'm going to start by writing out this little, what do you call that? I don't know. This little formula here, I guess, little cheat formula. So you're going to go over 100, so you're going to make a line and then the denominator is going to be 100. That's always going to be there. And then it is asking what is the percentage. So I know that I'm finding the percentage here. And so this percentage numerator is what I'm looking for. So I'm just going to put the percentage in there. That's what I'm solving for. And then I'm going to look for the word is. So it says that there are 6 males in a class of 20. So the word are here is going to be synonymous with is, of course. And so we're going to put 6 in the is spot and just treat this like it's the word is. So it's not grammatically correct, but it's mathematically easier to understand. So if there are, or in this case is, 6 males, so since we're using that word is for representing the 6, we're going to put the 6 as the numerator there. And then it says in a class let me mark off the is 6. And then in a class of 20. So we're going to put 20 in the of spot here. And then you're just going to solve like you would solve any proportion. So you're going to go this way first. So you're going to multiply the 6 times 100. So if I do 6 times 100, I would get 600. And then I am going to take that 600 and divide by what's left, which is the 20. So 600 divided by 20 equals 30. And that is going to be my answer, 30%. So on my answer line, I must write the percentage sign for full credit. And that's true of all the symbols and statistics and signs. They all are required. They all are important. So we have to write them all down. Okay, number 2, how many students in a class of 20 would constitute 62% of the class? So for this one, I am going to write down my little cheat formula. The 100's always there, so then I'm just going to kind of fill in the rest. So it says, how many students in a class of 20? So of 20, so I'm going to put 20 in the of spot, would constitute 62%. So it's giving me what goes in the percent spot, the 62%. And so what I'm solving for here is the is. So I'm going to go across like this, diagonally, 62 times 20. So 62 times 20 equals 1240. And then I'm going to take that 1240 and do the rest, so divide it by the 100. So 1240 divided by 100 equals 12.40. So I'm going to put 12.40 on line 2. And there we were finding how many students were in a class of 20, so we weren't looking for a percentage, so we don't need any symbols there. And then for number 3, it says if n equals 1 in a class of 20, what is the percentage? So now is a good time to remind you that n is the number of observations. And normally in the social sciences, the number of observations refers to like the number of people in your study. And you're observing each one of them. So each one would count as an observation. But at any rate, if n equals 1 in a class of 20, what is the percentage? So what we're going to do is write our little cheat formula again, and always we put the 100 there. And then we are going to put the 20 in the of spot, because it's saying of 20. And it's asking what is the percentage, so we're going to be solving for this percentage. And it's saying if n equals 1, so that's basically the same as saying if n is 1. So we're going to put the 1 in the is spot, and then we're just going to multiply across. So 100 times 1 is 100, and then we're going to do the rest of the formula, divide by 20. So 100 divided by 20 is 5, and this is our percentage that we were solving for, so we're going to write 5% there. Okay, and then number 14 says 18 is 60% of what? You could use this formula to solve for that, but you could also use our little cheat formula that we've been doing, so we'll just keep going with that. And so for number 4, I'm just going to write it a little lower. I'll draw an arrow. Okay, so we are going to put the 100 in the 100 spot, like we always do, and then we are going to, it's saying 18 is, so we're going to put the 18 in the is spot, 60%, so 60% is going to go in the percent spot, and then it's saying of what, so we're solving for the of portion here. So we're going to go 100 times 18, and that's going to give us 1,800. And then we're going to take 1,800 and divide it by 60, and that is going to give us 30. So our final answer for 4 is 30, and there's no percentage there because we were solving for a whole number. All right, now we're going to move down to the changes in percentage. And so for changes in percentage, we use this formula here, which is new minus old over old times 100. And so if you look at the word problem, it says if the unemployment rate was 5% and is now 7%, what is the percentage change? And so at first glance, most of us would probably think like it's 2 because there's a difference of 2. But we're not looking for the absolute value of the change. We're looking for the proportion of the change. So to calculate that, we're going to use this formula here. And in the word problem, the old and the new have been labeled for us. Sometimes you just have to identify old and new on your own using common sense. So if they give you like years of the percentages, you could look for those years and look in which one's older, and that's going to be your old, and which year is more recent, and that's going to be your new. So sometimes you have to just kind of apply a little common sense, but in this case they're labeled, and so we just plug those into this formula here. So the new is 7%, so we're going to write 7, and then the old is 5, so we'll write 5, and then we're going to divide that by the old, so we'll write 5 again. And then we're just going to start solving through. So 7 minus 5 is 2. And then we're going to pull that 5 down. And when we divide 2 by 5, we get 0.40. And then we're going to multiply that 0.40 by 100. And that's going to give us 40%. But we're not done yet. We have to put the word increase or decrease after our answer for full credit. And so here we are seeing the percentage go from 5 up to 7, so that's an increase. So we would write 40% increase, and we want to make sure we write that on our answer line, 40% increase. Okay, so now we'll look at percentage decreases. We're going to use the same formula again. And so we are going to take the new, which in this case is 5%. Oh, we better read the word problem. Say the rate was 7% old and is now 5% new. What is the percentage change? So we'll plug these values into that formula. So the new is 5%, so I'm going to do 5 minus the old of 7 over the old. So again, we'll plug in 7. And when we do that, we are going to get -2 from the 5 minus 7 over 7. And so when we do that division, we get -0.2857142. So this is what we talk about when we talk about rounding rules and rounding at each step of the calculation. So I'm just going to write down the 3 digits after the decimal, and then I'm going to look to the third digit to help me decide what to do with that second digit. And if the third digit is a 5 or higher, I'm going to round this up 1. So in this case it is, and so I'm going to round that up to -0.29. And then I'm going to go ahead and multiply that by 100 to complete the formula, and that's going to give me 29%. Now, technically it is -29%, but here what we have is a percentage decrease because it goes from 7% down to 5%. And so it doesn't make sense to say that we have a -29% decrease. So since the wording is required, we just go ahead and erase that negative sign. We don't have any negative percentages here on percentage change. And so then we're just going to do 29% decrease on our answer line. And again, you would have to put the percentage and the word decrease to get full credit. Okay, now we're going to look at determining percentage of change from raw scores, and it's the same exact way we did it with percentages. We use the change in percentages formula, but instead of putting percentages in, we just put in raw scores. So in 2009, the average cost of gas per gallon was approximately $2.64. And then in 2010, the average cost was $3.14. So I'm going to take this opportunity to just label my values so I'm very clear when I plug them into my formula on which is which. So 2009 is older than 2010. So the $2.64 amount is going to be the old, and then the $3.14 amount is going to be the new. And so now I'm going to just start plugging those into my formula. So new is 3.14, and that's going to be minus the old of 2.64. And then we're going to divide that by the old, which is 2.64. Okay, and then we're going to do the subtraction on the top, and when we do that, we're going to get 0.50. Divide that by the old of 2.64. And let me go ahead and get my calculator to show this. Okay, so then we're going to do the division there, 0.5 divided by 2.64 equals 0.189. I'm just gonna write down to the third digit after the decimal, but all final answers have to be rounded to 2 digits after the decimal. So I'm just gonna write 0.189 and then round it. So 0.189 would round to, I look at the third digit, if it's a 5 or higher, I round the second digit up 1 value. So a 9 is higher than a 5, so I'm going to round this to 0.19. And then I'm ready to continue with the calculation. So I'm going to multiply this by 100. And that is going to give me a 19%. And then I have to decide if that's an increase or decrease. So I'm just going to look at the old to the new, and the new number is bigger than the old. So that's going to be a 19% increase. And I'm going to write that whole thing on my answer line, 19% increase for full credit. Okay, and then I'm ready to do my per capita rates down here. So per capita rates are very useful in getting a good understanding of what's going on in a city or in a geographical location. So with the COVID crisis, you see a lot of, or we saw a lot of people comparing cities and states to one another. And it's not always fair to compare the number of people that have COVID in a populated area like New York City with a rural area in, I don't know, Texas or something, or Kentucky. So there's going to be less people in the rural area than there's going to be in the big city. And so it's not really appropriate to share like just the number of cases and do that in a way that's comparative. So instead what we can do is use per capitas, which is to make the playing field level, so to speak. So we say, all right, well, let's just take 100,000 people out of New York City and see how many of them have COVID. And then we'll take 100,000 people out of the rural area in Kentucky and see how many of them have COVID. And then we will compare the number of COVID cases per capita so that it's a fair comparison. So in order to calculate per capita rates, you have to use this formula here, which is the number of events. So that could be COVID cases or burglaries or robberies or whatever, divided by the population size times 100,000. So a per capita rate can be set at different amounts, but generally it's set at 100,000. It just kind of depends on what you're looking at. But if you're looking at large cities, that's certainly where the comparison is at, 100,000. So in order to calculate through this, we're actually going to have to break our rounding rules. So this is a rounding rule exception. So sound the alarms, woo, woo, woo. Rounding rule exception on per capita rates. Like I said, there's going to be 2 this semester. This is 1, and then there'll be a 1 later on, more towards the middle-ish end of the semester. So this is a rounding rule exception. So let's make a big deal out of it. Rounding rule exception number 1. We'll make a big deal so our brains don't forget that this case we round differently. And I'll explain why in just a second. So I'm just highlighting it, making it pop out so nobody forgets. Rounding rule exception number 1 on per capita rates. Okay, so generally in statistics, we work with really small numbers, and that's why we round to the second digit after the decimal. It matches the tables that we'll be using. You'll see that coming up. However, with per capita rates, we are working with really large numbers. And so if we rounded at each step of the calculation, basically we would end up with 0 as our answer. So I'll show you what I mean by that. So we're going to start with number 8, and it says to take the number of events and make that your numerator. So I'm going to do 144 robberies divided by the population size, which in this case is 160,000. And so when I do that math, I get, actually, let me do it. It's 0.0009, but let's see what's after the 9. Okay, nothing. So it's just 0.0009. So we're going to write 0.0009. So if we stopped and rounded here, then we would just be rounding this to 0. And so we would end up with a 0. So we're not going to round here. Normally we round at each step of the calculation, but we're not going to round here. We're just going to leave it as is. And we're going to finish out the formula by multiplying it by 100,000. And when we do that, that is going to give us a final answer of 90. And so we would say that there are 90 robberies per capita. For this, you just have to put 90 on the answer line. And then number 9 is a city of 500,000 reports 25 murders. What is the per capita rate? So I'm going to take the number of events, which in this case is 25 murders, and I'm going to divide that by the population size, which in this case is 500,000. And so when I do 25 divided by 500,000, I get 0.00005. So that's 4 zeros and then a 5. Again, I'm not going to round here because if I did, I would end up with 0. This is one of the only times we work with numbers this large. So then we're going to multiply that by 100,000. And that is going to give us a final answer of 5 murders per capita. So I'm going to write 5 over here on the answer line. Okay, and now I'm going to be solving through this table. You'll see something very similar to this on your homework. So pay attention and then you'll know exactly what to do when you get to that section. Okay, so we're going to calculate a decimal for each city, a percentage, and then a per capita rate. So we're going to start by taking the number of events, which in this case is the number of vehicle thefts in 2006 in San Bernardino. So we're going to do 2,917 divided by the population size, 338. And then when we do that division, it's going to give us a decimal, just like we got here. And so we're going to remember that we're not going to round the decimal on these per capitas. It's the rounding rule exception. So when we do the division here, we're going to get 0.0145603. And this is an instance where if you're using a basic calculator, this is what you'll get. If you're using a scientific calculator, you're going to get an extra digit, which might cause your calculator to round differently going forward. So just go ahead and write down the answer to the 1, 2, 3, 4, 5, 6, 7th spot after the decimal, because we're just going to try to get our answers to match, and by to do that we have to use basic calculators. And so you want your answers to match mine because that's what's in Canvas. So write the digits to the 7th spot after the decimal. And then what you're going to do is leave that alone. You're not going to round it. It's a rounding rule exception. And so then you're going to take that and you're going to multiply it by 100 to get a percentage, just like we did up here, multiplying 100 by our old versus new differences to get a percentage. So we're doing that again here. So we're going to take this decimal and multiply it by 100, and that is going to give us a percentage of 1.456. Okay, but now we do want to round to the second digit after the decimal, so we're back to our regular rounding rules. This column is not an exception. So we're going to look at the third digit to decide what to do with our second digit, and the third digit is a 6 or higher. So we're gonna, or I'm sorry, it's a 5 or higher, it's a 6. So we're gonna remove it and round up. So our answer is gonna be 1.46% there, okay? And then we're gonna go back to our decimal and we're gonna multiply it by 100,000. So when we multiplied by 100, we got our percentage. And when we multiply by 100,000, we're gonna get our per capita. So I'm gonna take this decimal and multiply it by 100,000. And when I do that, I should get 1,456.03. And you would say 1,456.03 vehicle thefts per capita. Okay, and then we'll do the same thing for this one down here. So we're going to take 426 divided by the population of Redlands, or the area of Redlands that they were studying, 70,625. When we do that division, we are going to get a decimal of 0.0060318. Again, writing 7 spots after the decimal. We're going to multiply that by 100 without rounding because of our rounding rule exception. And so when we do that, that's going to get us 0.60. We do round here. So 0.603 is going to round to 0.60 because a 3 is less than 4. And so we're not going to round that second digit after the decimal. We're just going to leave it and erase the 3. And then we're going to multiply that decimal by 100,000 to get our per capita rate. And when we do that, we are going to get 603.18. So there you see, if you had the extra digit here from using a scientific calculator, you would put it here, and I think it causes you to round up in this scenario, which would end up being incorrect. So make sure you're using a basic calculator or only writing to 7 spaces after the decimal and leaving it like that, and then going from there with your rounding. Okay, that's it for the percentages worksheet. So graphing is a really good way to demonstrate our descriptive statistics. If we can represent our data with graphs, it makes it more palatable for people. It's easier for them to understand. And so graphs are a really great way to communicate our findings. And so for graphing, there is an order in which you should move through steps to make a graph correctly. And so the first step is to make a distribution. And a distribution in this class can actually look a bunch of different ways. So a distribution, when you hear me say that word, it technically means an arrangement of scores in order of magnitude. And that could be just scores written out in order of magnitude, like you see on the slide in the example there. So we go around and we collect data and we ask the first student, on a scale of 1 to 10, how stressed are you? 10 being I'm freaking out, and 1 being I'm cool as a cucumber. And so the first student says 8, the next one says 7, the next one says 4. All those numbers create what we call a data set. And when we collect our raw data, that data set has a bunch of numbers that are out of order and random and just jumbled up. And so to distribute them means to just put them in order of largest to smallest or smallest to largest. So a distribution can just be all the scores distributed in order, or a distribution could be like a frequency distribution, which is kind of more organized numbers, and their numbers put in a chart. And so that leads us to step 2, which is to create this other type of distribution called a frequency distribution. So after you've distributed your numbers in order of magnitude in step 1, the next thing you want to do is make a column for all your scores in a chart. And then next to that column, you make a column for frequency. And then what you're going to do is put all possible scores, so all possible scores that a person could obtain, for example, and you put them in the first column, as you see here on table 1.3 on the slide under stress rating. And then next to the stress rating, you put the frequency count, which is just a simple count of something, a simple count of how many times each number occurs in your data set. So how many times did the number 0 get chosen? 1 time. according to the frequency distribution. How many times did a stress rating of 1 get chosen? 1 time. How many times did a stress rating of 10 get chosen? 3 times. And so a frequency distribution gives you that first column, which is all possible scores, and then the next column, which is the frequency of each score. Percent is added here, but that's technically not part of a frequency distribution. It's another descriptive on top of a frequency count. So when you make your frequency distributions on your worksheet or your homework, you don't have to put that percent column. All right, so step 3 is to make a graph, and a graph is another type of distribution because in the graph on the bottom of it, which we call the x-axis or the abscissa, we're going to put raw scores. So on that horizontal line, we always put our raw scores, and then on the vertical line, which is the y-axis or the ordinate, is where we put our frequency count. So all those raw scores that we put on the x-axis, they have to be distributed. So this is a distribution as well, and we refer to most of our graphs as distributions in this class. So when you make a graph, the first thing you have to do is set up that y-axis and set up that x-axis. Again, on the x-axis or the abscissa, you put your raw scores, and on the vertical line, which is the y-axis, or it's also known as the ordinate, you put your frequencies. So step 4 is to make a histogram, and a histogram is shown here on your screen on this slide. And so a histogram has a rectangular bar drawn above each raw score. And so what makes a histogram different from a bar graph is that a bar graph is used for a different type of data. So the type of data that we're using on a histogram is continuous data, which are numbers that kind of continue on forever is how I like to think of them. So just 0, 1, 2, 3. Whereas bar graphs are used for non-continuous, or what's more commonly referred to as categorical or discrete data, because it's data that's collected in the form of words or categories. So college major, favorite football team. And on bar graphs, not shown here on this slide, the steps between the values are separate. So each bar stands on its own, and that represents a category or categorical data. So histograms are used for continuous data, like I said, SAT scores, age, temperature. And this is where the steps between the values are not going to be visually drawn as separate. So you would see it kind of all one continuous line like here on the histogram. And then after you make a histogram, step 5 is to make a frequency polygon. And a frequency polygon, just like a histogram, is another distribution. And so with a frequency polygon, you are going to be plotting your dots the same way you plot them for a histogram, but then you're going to be connecting them in a different way, and that's what makes it a frequency polygon. So there's a single point used to show the frequency of each score, and then those points are connected with lines. It's especially useful when showing 2 distributions simultaneously. So if I'm taking the stress scores of our class and then another stats class I have, and I want to reflect both of those distributions on one graph, a frequency polygon is a really great way to do that because you can just put the lines in different colors, and then it's easy to see the comparison between them. But I'll show you that on the worksheet coming up. Okay, so here are some terms that you need to know. We're not going to really be doing anything with these 2 types of graphs in terms of calculating data points or plotting them or anything, but you just need to know them mostly for the multiple choice section of quiz 1. And so the other type of graph that I want to talk about is called the stem and leaf graph, and it's just another way to graph data. It's another type of distribution. And so in the you make this kind of chart here where in the first column you have the stem, and then in the second column you have the leaf. So you put the first digit of the score in the stem column. For example, if you look at the highlighted numbers on the slide, 9 represents scores in the 90s, and then below that, 8 would represent scores in the 80s, 7 in the 70s, 6 in the 60s, and 5 in the 50s. And then you put the trailing digit in the leaf column. So if you look again at the scores that are highlighted in yellow, what we would actually see from this graph is that we have a score of 90 and we have a score of 94. In the 8 or in the STEM column with the 8, we have scores of 83, 84, 85, 87, 89. And then look at the STEM column for number 7. We have 70, 72, another 72, and then a 79. And then we also have what are called wow graphs. And wow graphs are deceptive graphs that occur due to not setting the base of the ordinate at 0. Basically, if you don't put the base of the ordinate at 0, it creates like a zoom effect on the graph, and that makes the data look way more dramatic. You can see that represented on these two frequency polygon images down here. So some corporations will hire statisticians to create wow graphs to make like their annual sales reports look better, or to make anything look more dramatic. I've seen wow graphs with the COVID crisis, in some cases making it look worse than it is, and sometimes making it look not as bad as it is. So wow graphs are out there. Just look for them. You'll find them in the media. It's just any time that base of the ordinate is not set at 0. They're trying to zoom in on that graph and make the visualization of the data a lot more dramatic. All right, so we're going to do the graphing worksheet now. Go ahead and get that off of Canvas so that you can follow along, and we'll do it together. Okay, this is the graphing worksheet. So we're going to go through the steps of graphing, and step 1 is to distribute your scores or put them in order of magnitude. You can go from largest to smallest or smallest to largest. It really doesn't matter. But in this case, I'm going to go from largest number to smallest number. And the way I like to do it is I write down the largest number, which in this case is 100, and then I cross it off. Then I have another 100 down here, so I'm going to write that down and then cross it off. And then I'm going to write the next number, which is 95. And so 95 is here. And there's only one of those, and then the next number is 90. And it looks like there are 2 90s. So there's the other one. And then 85. And 85. Okay. And then I have 80. And there are 4 80s. So 1, 2, 3, 4. Okay, and then I'm on 75. So there are 1, 2, 3, 4, 5. Okay, and then 70s next. So 70, 70, and 70. Okay, and then all that remains is this one, 65. Okay, so now I have distributed my data and I have put them in order of magnitude, in this case from largest to smallest. The next step is to make a frequency distribution. So for the frequency distribution, I'm going to write all possible scores once. So people got 100, people got 95, people received a 90, an 85, 80, 75, 70, and 65. And then the column next to it is labeled F for frequency, which is just a simple count of something. So the number of times 100 occurs in this data set. So here we have 100 in the frequency column. We're going to put the number of 100s in our data set. And here we have 1, 2. So in the F column, I'm going to put a 2. And then I'm going to count my number of 95s. There's just 1, so I'll put a 1 for 95. Then I'm going to count my number of 90s, and it looks like there's just 2 90s, so I'm going to put a 2. And then 85, 1, 2. 80, 1, 2, 3, 4. 75, 1, 2, 3, 4, 5. 70, 1, 2, 3. And 65 is 1. So that is step 2 to set up my frequency distribution. And now I'm ready to go ahead and start graphing. So the first figure I'm going to make is a histogram. And so in order to make the histogram, I have to start by putting my raw scores on my x-axis, or my abscissa, as it's called. So x-axis, it's also known as abscissa. Did I spell that right? No. Oh, I missed an S. There's an S here. Whoop. Okay. X-axis, abscissa, and then what we put on there is the raw scores. And so the raw scores go here on the x-axis. So we're gonna start from left to right. And so we're gonna put all possible scores going lowest to highest. We always go lowest to highest on our graph. So 65, 70, 75, 80, 85, 90, 95, 100. And then on our y-axis, also known as the ordinate, we put all of our frequency counts, which we had already laid out on our frequency distribution. And so we're going to start at the base of the ordinate with a 0, as always, so we don't end up with a wow graph. And then we are going to just go up by 1. And I could just go up to 5 because that is the highest number that I have, but I'll just go all the way for funsies. All right, so now we're ready to plot our data, and that is to make dots at the intersection of the two values. So for 65, we have a frequency of 1. So I'm going to go to the 65 raw score on the x-axis and the frequency count of 1 on the y-axis. I'm gonna move my fingers together, and I'm gonna put a dot at the intersect. And then I'm just gonna keep doing that for each one. So 70 is 3, put a dot at the intersect. And 75 is 5. And there were 4 80s. And there were 2 85s. And there were 2 90s, 1 95, and 2 100s. Okay, and so for a histogram, the way you connect the dots is continuous, meaning you don't separate each bar, but instead they run into each other. And so the way that we symbolize the beginning of a histogram is going to the middle of the first cell, putting your pencil on the abscissa, and then you go up to the line that the first dot is on, go over, cross through that dot into the middle of the cell after it, and then you go up or down, but in this case up to the line that has the next dot. Then you're gonna go over through that line to the middle of the cell after it. We gotta go up to the next dot, over through the dot to the middle of the line. My next dot is on a lower frequency, so I'm gonna go down, cross through the dot to the middle, down, cross through the dot. This one's on the same line, to the middle, down, cross, and then we go all the way down to touch the abscissa. And then what's always fun is to shade it in so people can clearly see it. Oopsies. Okay, there we go. So it's gonna outline, and then you can just shade it in. It makes it real easy to understand the data. It's a nice visual representation. You can see how the dots are kind of corresponding with each other, where they're falling in relation to one another. All right, that's pretty good. Okay, and so the next figure that we're gonna make is a frequency polygon. And so down here, I'm gonna write the word frequency polygon so I remember what I made. And then on the abscissa, I'm going to put all possible scores, which again was 65, 70, 75, 80, 85, 90, and 95, and then 100. So I'm setting it up the exact same way I set up my histogram. I'm going to put 0 at the base of my ordinate. I'm going to put all my possible frequency counts plus some right there. Okay. And so then we're going to just plot these data points again, but the way we connect them this time will be different, and that's what will make it a frequency polygon. All right, so there was 165, there was 3 70s, there were 5 75s, 4 80s, 2 85s, 2 90s, 1 95, and 2 100s. Okay, so the way we connect the dots with the frequency polygon is that we start at the intersect of the abscissa and the ordinate, so in this lower left corner, and then we just connect the dots. Try to be as straight with your lines as possible. All right, and then when you get to the last dot, to indicate the end of the frequency polygon, you go to the intersect of the 0 frequency and the abscissa, where you just go down to the abscissa. That's another way I could have said that. And that lets the reader of your chart know that that's the end of the frequency polygon. And so what's nice about a frequency polygon is that if you wanted to show different groups of people, you could get another sample and then represent it with another line in another color. And so it's nice to compare samples using frequency polygons because you can get a bunch of lines on there to clearly show the comparison. Okay, so we have been discussing the idea that when we take our data and we distribute it, we have a distribution. And so the way we present those distributions could be in just numbers in order of magnitude. It could be in charts. It could be as histograms. It could be as frequency polygons. But however we display them, as long as the numbers are put in order of magnitude, it's called a distribution. And so we use these distributions all throughout the semester. Kind of a lot of the theoretical concepts in this course are based off of what we call the normal distribution. And so we're going to talk about that now. And I just would like to say that I remember when I was a student and we got into talking about these normal and kurtotic distributions, and anytime we talked about the normal curve, my immediate reaction was just to tune out and start thinking about what I was going to have for lunch. But you can't do that. It really came back to bite me in the butt. You have to learn and understand and come to love this normal distribution. We call it a normal curve, because if you can understand the normal curve, it really helps the rest of the content in this course, the calculations, the statistical analyses, the reasons why we're doing the tests that we're doing. All of it. It makes it a lot clearer if you have a good understanding of the normal curve. So we're going to start those discussions now, but we'll talk about normal distributions all semester long. All right, so a normal curve is referred to as a mesocurtic shape, a bell shape. It's also sometimes referred to as the Gaussian curve, because this guy that you see on the slide here, Carl Gauss, is the gentleman who kind of discovered the normal curve and then also termed it. So at any rate, the normal curve, or the mesocurtic shape, you could see it down there on the bottom left of your screen, is bell-shaped and symmetrical. It's not always perfectly symmetrical. In theory, it's perfectly symmetrical, but when we plot our data and make a frequency polygon, it doesn't normally look perfectly symmetrical. So we're looking for mostly symmetrical in this class, and we'll count that as symmetrical. But the normal curve is going to serve as our standard of comparison all semester long. We're going to be getting distributions from our sample, and we're going to be comparing those distributions to the normal curve. So the normal curve is the standard of comparison because distributions that are observed in nature usually take this shape. And so if you think about the shape of a mesocurtic curve, what that is showing you is that lower numbers have a lower frequency, higher numbers have a lower frequency, but then middle numbers tend to have the highest frequency. So in other words, most of us behave in kind of a moderate way And most of us are behaving in the same way. And then if our behavior, that's being studied with our sample, is falling in these tails of the curve, the left and the right, where the frequency is 0, then that is where the outliers are, or the people that are statistically significantly different from the rest of us normal, average people that are in the middle. So that's kind of the basic idea behind the mesocritic shape, and we do get that by collecting our data, recording the frequencies of it, and then plotting it just like we did in the graphing worksheet. The word kurtosis is defined as the extent to which a frequency distribution deviates from the normal curve. So I like to think of kurtosis as a diagnosis. If a curve is not normal, then it's sick. It has kurtosis. And so there are two types of kurtosis. Leptokurtic and platykurtic. And so you can see leptokurtic in the middle there. The dashed lines are the normal curve, so you can visually see the comparison between the two. But the leptokurtic shape is high and peaked, and there are actually more scores in the tails, the left and right side of the curve that are at 0 frequency. There's more scores in the tails than there are in the normal curve. And then there's a platykurtic, or I like to think of it as flatykurtic shape, a kurtotic shape. So platykurtic is low and flat, and there are less scores in the tail than the normal curve with platykurtic shapes. So what you want to be able to do so that you're prepared for the quiz is be able to look at these shapes without the captions underneath them and identify which is which. So try to identify which curve is mesokurtic, leptokurtic, and platykurtic just by the way the shape looks or the way it's described. So other non-bell shaped or kurtotic, non-normal shaped distributions. So those include the unimodal distribution with exceptions, and then the bimodal and rectangular distribution. So in a unimodal distribution, if it's non-bell shaped, it's going to look like a leptokurtic shape where you have one value that's clearly occurring more than any other value. But a normal curve can be unimodal in nature as well. You have that one value that's in the middle and it's occurring more than the others, but it's just not occurring more as significantly as you would see in some leptokurtic shapes. And then we have the bimodal distribution, which is where two values clearly occur more than any other. They don't have to be even, but as you can see here on B, image B on the slide, there are two values that are at the peaks, and so those two are occurring more than the others. And then we have a rectangular distribution, and that would look like figure C, where all the values are occurring pretty equally. Okay, so like we talked about, usually distributions look normal or symmetrical, mostly symmetrical, we might say. And so in a skewed distribution, a distribution is not symmetrical. And the side with fewer scores is considered the direction of the skew. So you could look at the bottom of your screen here, and you could see a symmetrical curve on the left, and then in the middle, a non-symmetrical curve. You can see that there is a number that is pulling the tail of the right side of the curve towards it. So in the middle, we would say that that distribution is non-symmetrical and it's skewed to the right. So if a graph or a distribution is skewed to the right, we say that it is positively skewed. If a distribution is skewed to the left, as you see on the bottom right image, where the tail on the left, there's a score there that is pulling that tail towards it. And so we would say that that shape is negatively skewed or skewed to the left. So the way I remember that negatively skewed means that the tail is skewed to the left is I think of that Beyonce song. I don't know if you know it. It's older, but it goes to the left, And sorry, I can't sing. I feel like I've disgraced Beyonce. That's terrible. But anyways, she sings to the left in that song, and it means that she's dumping her boyfriend and he's got to go, right? So that would be negative if that happened to you. So that's how I remember negatively skewed. Skewed to the left, that's negative. That's bad. All right. Usually this happens when what we're measuring has an upper or lower limit. Like, for example, how many kids do you have? You can't have less than 0 kids, so the distribution would probably look more positively skewed. But at any rate, the normal curve, the distribution that we use as comparison in statistics, is symmetrical. Okay, so central tendency allows us to kind of summarize what's going on in our data set with one number. In other words, how can a group of scores be summarized with a single number? The answer is central tendency. And central tendency is the typical or most representative value of a group of scores. And central tendency includes the mean, median, and mode. So we're going to learn about what they are now, and then we're going to use our graphing worksheet to calculate them for practice. So the first measure of central tendency is the mean. The way you calculate the mean is by summing all of the scores. Sum is another word for adding them up, and then dividing by the number of scores that you added up. So if you look on the slide, you see the formula there, and there's some statistical symbols and letters that we need to define. So if you see that one symbol that looks kind of like an E, that's called sigma, and it means summation of, or add everything up after me. So in this formula, it's telling you to add up all the x's. X stands for the raw score. So X is the score that you are collecting for your data set. N stands for the entire number of observations. Usually that's just the number of people that you have, is what we mean by observations. And then M stands for the mean. So if you look at the bottom right of the screen, you'll see an example there where they added up all 7 of those values highlighted in orange. They got 32, and then they divided 32 by the number of numbers they had just added together, which was 7. So 32 divided by 7 gave them a mean of 4.57. Notice how it is rounded to the second digit after the decimal. The mean is the most stable measure of central tendency because all the scores in the distribution are included in its calculation, which, as you'll see coming up, is not true of the mode or the median. The mean is used with equal interval variables, and equal interval variables just means that there's an equal amount between each number. So the distance between 1 and 2 is the same as the distance between 2 and 3, 54 and 55. So equal interval variables are things like age, weight, GPA. The next measure of central tendency is called the median. The median is symbolized there with a MDN, and it's the middle score in your distribution. So what you have to do is distribute all your numbers from highest to lowest or lowest to highest, and then you just identify the scores or score in the middle. If it is an n that is an odd number, then you're just going to have that one score in the middle, and that's going to be your median. But if your n is an even number, then you're going to have 2 numbers in the middle, and you would have to calculate the mean of those 2 numbers. And the answer that you get there is going to become your median. So if I had 50 and 50 as my 2 numbers, I would add 50 plus 50 together, get 100, divide by 2, because I used 2 numbers in my calculation, and I would end with 50. It's possible to get like 45.5 or whatever. All right, so it is better to use the median than the mean if there are extreme scores, which are also known as outliers. So this is heavy on the quiz, and it's on the final exam, so you'll want to know this. You can kind of get a understanding of what I'm describing if you calculate the mean, median, and the mean and the median for those scores. If you calculate the mean and you include all 5 of these scores in it, you're going to also include that outlier of 2.32, and that is going to positively skew your data to the right, because that outlier of 2.32 is pulling the mean towards it. So the mean is going to be a higher number than the majority of the numbers there. It's going to be like 1 point something, I can't remember. You'll calculate it, you'll see, right? So add them all up, divide by 5. It's going to be a number that's 1 point something, which is not representative of the majority of the data there, right? Most of the data is less than 1, so a mean that's over 1 is really not representative. And so we want to use the median when we have an outlier like we have here with the 2.32. So if we put them all in order, then the middle number is going to be 0.81, and that number better represents the majority of our data. So we like to use the median if we have outliers, and also if we have rank ordered variables. So if we are ranking our variables in order, like first place, second place, third place, if you ask someone what's your favorite type of food, put these in order, and you give them french fries, pizza, and hot dogs, and they have to rank each one, we would use median to describe the central tendency of that measure. And the last measure of central tendency is the mode. It's symbolized by MO, and it's just the value with the greatest frequency in a distribution. So when you make your frequency distribution, you just have to find the highest number in the F column, find the associated score, and that's going to be your mode. It's also going to be the highest point on the histogram or the frequency polygon. In a perfectly symmetrical bimodal, so when it has 2 data points that are clearly scoring more than any other, in a perfectly symmetrical bimodal distribution, the mode and the mean are going to be the same. If the distribution doesn't look this way, then the mode is usually not representative of that data. So the mode is actually the least used measure of central tendency in statistics. It's used with nominal variables, so variables that are categories like gender, eye color, favorite sports team. When people are responding to your survey questions in words, you have nominal variables. We'll talk more about the different types of variables later. The main thing you need to know is the mode is the value with the greatest frequency in the distribution. Okay, so we're going to go back to our graphing worksheet now, and I'm going to show you how to calculate these measures of central tendency using the data from that worksheet. All right, and so now we're going to do the central tendency portion of this worksheet. And so to do that, we're going to need to calculate our mean, median, and mode. And so we'll go ahead and start with our mean calculation. So our mean calculation is sigma x over n, which is our number of observations. And so in order to get sigma x, I need to add up all these raw scores. And so I could just go in my calculator and enter them in one at a time. But if I did it that way, I would have to enter in 20 scores, because the n here is 20. There are 20 numbers. In fact, let me write that off to the side so I have that info handy. And so instead of having to calculate 20 numbers or plug 20 numbers into my calculator, I can do a little quick math, multiplying and then adding, and that way I won't have to put as many numbers in my calculator, and so there's less room for error. So the way I would go about getting sigma x then is kind of working smarter, not harder. So I would do 100 times 2 equals 200, and then I would do 95 times 1 is 95, and 90 times 2 is 180, and 85 times 2 is 170, and 80 times 4 is 320, 75 times 5 is 375, 70 times 3 is 210, and then of course 65 times 1 is just 65. And then I could just add up all these values here. And so instead of adding 20 values, I'm just adding 1, 2, 3, 4, 5, 6, 7, 8 values. And so when I add those up, I get 1,615. But in order to get the mean, we do have to divide by n, which we already determined was 20 because we counted 20 scores, or 20 observations as they're sometimes referred to. And so when I divide 1615 into 20, that gives me a mean equal to 80.75. So I'm gonna just go ahead and write that over here so it's clear that my mean is 80.75. Very good. Okay, and then I'm gonna calculate the mode. The mode is symbolized with MO, and the mode is just the number that occurs the most. So all I have to do is look at my frequency distribution, find the highest frequency, which in this case is 5, and then see which score it's associated with. And in this case, it's associated with 75. So the mode is 75. It is possible to get 2 modes, 3 modes, 4 modes, if there were 5 75s, 5 80s. So I would just write down each mode if there's multiple. But in this case, there's just one. And then the last calculation we're going to do is the median, which is symbolized with MDN. And so in order to calculate the median, you must first distribute your numbers in order. If you don't distribute them and you just take your random data set and just pick the one in the middle, you're gonna get the wrong answer. You have to first put them in order. And so then what you can do, since I have an n of 20, it's an even number, so I could just count 10 up and 10 down and then circle the 2 in the middle. When it's an odd number, it's super easy because you just find the one number in the middle and that's your answer. But when you have an even n, you have to do one extra step. So here, if I count to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's going to be this 80 here. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's going to be this 80 here. So I have these two 80s in the middle for the median spot. And so when I have 2 numbers in the middle, in this case, they're both the same. So the answer is obviously going to be 80. But if I had 2 in the middle that were different, what I would do, and you know what you can do here too as well, is take the mean of those 2 values, and that's going to be our median. So if I add 80 plus 80, it's 160, and then I divide by the number of numbers in my mean calculation. So I would divide that by 2. You know what, let me do it this way so it's not so messy. 160 divided by 2 is 80, of course. It is possible to get like, you know, a 0.5 answer or a 0.25 answer, not, you know, with these nice round whole numbers that are the same, but in different scenarios, you can get 2 digits after the decimal. Okay, so the median then is 80. And that's how you calculate measures of central tendency. Okay, so this slide is very important in our lives. We need to save this slide. Make sure we have it handy when we take the quiz. There's a large portion on quiz 1 that you will find the answers to on this slide. So if you look at the slide, you'll see figures A, B, and C on the right. I'm going to start by talking about C. If the distribution has little or no skew, we remember skew is caused by outliers or extreme scores. If the distribution has little or no skew, then the median, mode, and mean should all be the same or close. It should be a normal curve. It should be a normal distribution. However, in skewed distributions, due to extreme scores, the mean is pulled toward the tail of the distribution and is unrepresentative of the body of scores. The reason it's pulled toward the tail of the distribution is because in a mean formula, all values are included. If you have an outlier in there, it's going to pull the number, it's going to pull the mean towards it. So if the outlier is a high positive number, the mean's going to become a higher, more positive number. And then if the extreme score or the outlier is a extreme like low number or negative number, then your distribution is, or the mean of your distribution is going to be pulled that way. So now go ahead and look at A. In a negatively skewed distribution, the mean is lower than the median, so you can see that reflected there. So if I have a negatively skewed distribution, or like we see in A, where the tail is being pulled to the left, you can then see that the mean is lower than the median. It's going to be a smaller number than the median. Whereas with B, We have a positively skewed distribution, and you can see that it is skewed to the right because the tail is on the right, and it's being pulled that way by an extreme score. That's a high positive number, and so the mean is going to be higher than the median in that case. So if you look at B, you will see that the mean is kind of on the side that's closest to the tail because it was pulled that way by the outlier, whereas the median and the mode are kind of further to the left. So B is an example of a positively skewed distribution, and in that case, the mean will always be higher than the median. And with A, we have a negatively skewed distribution where the mean is lower than the median. It's a smaller number than the median. It doesn't have to be a negative number, it just has to be a smaller number. And it's being pulled to the left. The mean is being pulled to the left because there's an outlier on the left. It's pulling it towards it. All right, so make sure you have a good understanding of this slide for the quiz. And that is it for Chapter 2. Thank you for listening. I will talk to you on the next one. Have a great day.